We're continuing with our parametric equations now. We're going to work on eliminating the parameters today. It says we can determine the equation for a parametric equation in Cartesian or rectangular form by eliminating the parameter. So we're going to change it from a parametric equation to the functions that we're used to with a Cartesian. This can be done by solving one equation for t, choose the easiest one to do that, and then substituting that expression into the other equation. That's going to get rid of our t variable and take away from the parametric. All right, so for our first example here, we have x equals -2 plus t and y equals 5 minus 2t. The easier one to solve for t here would be this first one. So that's the one we're going to solve for t. On this first one, the only thing I need to do is add 2 to get it to the other side. So I get x plus 2 is equal to t. Now that I know t is x plus 2, I can plug that in for t in the other equation. So we get y equals 5 minus 2 times t. When we substitute, I have put parentheses there because I'm only going to substitute the t for x plus 2. Everything else stays the same. Now we simplify, so I'm going to distribute to get rid of this -2. -2 times x gives me -2x, and -2 times 2 gives us a -4. Our last step is to combine our like terms. And so I've got a -2x, and then 5 and -4 gives me 1. And so this would be our rectangular Cartesian form of the equation. It no longer has a t in it, so it just has the x and y. All right, let's try another one. For our next one here, we've got y equals t minus 5. So in this case, that's the easier one to solve. All I need to do is add 5. So we get y plus 5 is equal to t. And now we can do our substitution. So we get x is equal to y plus 5 squared. I distribute, and remember y plus 5 is squared is the same thing as y plus 5 times y plus 5. So we have to FOIL that. So we get y squared plus 5y. Actually, let's solve for y by square rooting. Sorry about that. I don't know why I tried to make that harder. We can get rid of the square by taking the square root of both sides. So I get the square root of x is equal to y plus 5. So I took the square root here of both sides. And my last step is to subtract the 5. And so we get y equals the square root of x minus 5. All right, these take a few more steps just because there's a coefficient in front of it, but it's still the same process. So we're going to pick one of them to solve for t. I'm going to go ahead and do the x one here. And so I subtract my 2 as my first step, and I get x minus 2 equals 6 times t. I divide by that 6. And so we've got t is equal to x minus 2 over 6. Now we're ready to plug that into our other equation. Remember, I'm only substituting the t, so that -4 stays there, and I get x minus 2 over 6, and then the plus 5 at the end. So I've only replaced that t with the t from the other equation. And so now it's time to distribute. And so we get -4x plus 8 over 6 plus our 5. -4 times x gave me that -4x, -4 times 2 gave me that +8. This can be reduced because 2 goes into all of them. So the reduced form of that would be -2x plus 4 over 3 plus 5. And that's a perfectly good way to leave the equation. All right, number 4 puts it in a word problem form, but the process is still the same. It says the equation of the trajectory of a rocket fired on level ground is given by the parametric equations x equals 25t and y equals 10t minus 5t squared. What is the rectangular equation of the trajectory? So again, anytime it's asking you for that rectangular equation or in the Cartesian form, it's asking you to get rid of that parameter, the time. So I'm going to go ahead and take this first equation. That's going to be the easier one to solve for t. They're being multiplied, so all I do is divide by 25. So we get x divided by 25 is equal to t. And that's what I'm going to want to substitute into the other equation. So we get 10 times my t, which is x over 25. Again, I'm putting that in parentheses just to show the only thing I'm substituting is the t. Minus 5 times x over 25 squared. Again, the only thing I'm substituting is that t right there. It's t squared, so we're going to leave it as t squared. Just the t being x over 25. So we're going to go ahead and simplify this, and we get 10x over 25 minus 5 times x squared over 625. I went ahead and squared both of these, x squared and 25 squared. I can reduce this by 5. So that's going to give me 2x over 5. Oops, that's a minus, that's not a plus. And then I get 5x squared over 625. And that too can reduce, so we're going to go one step further to reduce that. You can't see that. And so we get x squared over 125, because the 5 goes into 625 125 times. And so this would be our rectangular form or Cartesian form of the equation. We're going to look at some that we're going to have to really use all the math that we've learned previously in order to eliminate the parameter. In here, it tells us with conic sections that we've done in the past, we can eliminate the parameter using that in trig functions. To do that, we're going to go back and think about some of the identities we learned in the trig section, like cosine squared of theta plus sine squared of theta is 1. We told you that was a really important trig identity you wanted to make sure that you remember. And so with that being said, x squared is equal to cosine squared of theta, and y squared is the same thing as sine squared of theta. So you're going to want to think through those. Another identity that we learned that we said was also pretty important, that's secant squared of theta minus tangent squared of theta is 1. And we want to let the positive term equal to secant squared theta and the negative term be tangent squared of theta. This will graph a hyperbola, it tells you. The other one will graph an ellipse, but we'll see how that works in a second. So if we want to write a conic equation for each parametric equation, because that's going to get rid of my t, I look at these equations here and see how I can do that. So on this first one, I would want to divide by 3 on both sides to get that cosine of t by itself. So I get x over 3 is equal to cosine of t. I'm also going to do this on the second one since it has a coefficient of 3. And so we get y divided by 3 is equal to the sine of t. Now that we have cosine and sine by itself, remember up here we said cosine squared plus sine squared is equal to 1. So we can set that x over 3 squared plus y over 3 squared is equal to 1. Since this is cosine, x over 3 is cosine, and y over 3 is sine, then cosine squared plus sine squared is equal to 1. That got rid of our t parameter in there. We would want to simplify this a little bit further, so we get x squared over 9 plus y squared over 9 equals 1. Since these are both the same, I would multiply this whole equation times 9, and I get x squared plus y squared equals 9. And we know that is a circle. So the conic sections are some parametric equations that we've removed that parameter from. We're going to try a couple more of those just so that you can see how that works. And then we'll work some backwards. So again, here I would want to divide by 5. So I get x divided by 5 is equal to cosine of t. And y divided by 6 is equal to the sine of t. So I've gotten my trig functions separated by themselves, isolated. And so now I can do the x over 5 squared plus y over 6 squared is equal to 1. That's my cosine squared plus y squared plus sine squared is equal to 1. That gives me x squared over 25 plus y squared over 36 is equal to 1. And we know that when it's equal to 1 with the different coefficients, that's an ellipse. So just to review what you did in those conic sections, just so that you can recall those. All right, right here, we've got a little bit more work to do, but it's the same concept. There we go. All right, so the first thing I'm going to do here to get this cosine t isolated would be to subtract the 3 to the other side, and then we would divide by 4. So we get x minus 3 over 4 is equal to the cosine of t. For this one, I would add the 4 to get it to the other side, so we get y plus 4 divided by the 2 is equal to sine of t. You're always going to want to isolate those so that you can put them into the identities. The identity that we're using is still the same because that's a cosine and a sine. We can do cosine squared plus sine squared is equal to our 1. So in this case, we get x minus 3 over 4 squared plus y plus 4 over 2 squared equals 1. When we simplify that, we can leave it as x minus 3 squared over 16 and y plus 4 squared over 4 is equal to 1. Because you should be able to identify that again as an ellipse in standard form. All right, we'll try a couple more. On number 8 here, it's got secant and tangent, so you'll get to see what that looks like. For my first one, I would want to divide by 4 to get rid of this one. So we get x over 4 is equal to secant of t. And then the y is already solved here, so there's nothing we have to do with that one. Now our identity was secant squared of theta minus tangent squared of theta is equal to 1. So we're going to get x over 4 squared minus y squared is equal to 1. So I've plugged that in as secant squared minus tangent squared is equal to 1. When I simplify this, I get x squared over 16 minus y squared is equal to 1. And we can recognize that as a hyperbola since it's got the minus in the middle. All right, one more with a few more steps. Again, we add the 4 to get it to the other side. So we get x plus 4 and then divide by 3. And then over here, we get y minus 6 over 2 is equal to the secant of t. Now it told us there to make sure that we put the secant first, since it's secant squared of theta minus tangent squared. So in this case, we would get y minus 6 over 2 squared minus x plus 4 over 3 squared equals 1. And when we simplify that, that's going to give us the y minus 6 squared over 4. X plus 4 squared over 9 is equal to 1. Again, that's a hyperbola because it's got the minus. This one just happened to have a center at negative 4, 6. Remember, that was the center, that HK. And then the bottom part was what told us to go left and right. All right, the last thing we're going to do is write a set of parametric equations for each of the conic equations. So now we're going to go backwards. We're going to get that t going back. And so we need to recognize some things as we work on this. So when we get x squared over 4 plus y squared over 1, we can recognize that that is x over 2 squared, or y over 2 squared is equal to 1. And so we know that cosine squared of t plus sine squared of t is equal to 1. And so this part right here would have to be our cosine. So we get x over 2 is equal to the cosine of t. And y over 2 is equal to the sine of t. We multiply both sides times 2 to get that x by itself. So we get 2 cosine of t. Same thing over here, and we get y equals 2 sine of t. And so that would be our parametric equation with our parameters of t. We would do the same thing on this next one. You recognize that that is x over 4 squared plus y over 7 squared is equal to 1. And so this part right here would be our cosine. This part would be our sine. And so you should recognize x equals 4 cosine of t. and y is equal to 7 cosine of t. That would be our parametric equation. So we've added that parameter back in, and so we've got the t variable in there for time. All right, so this one looks a little bit longer, but still the same concept. You have to recognize what is being squared on each one of these so that we can put it back into our identity here. And so for our first one, we've got x minus 3 over 7 squared. For the second one, we have y plus 2 over 6 squared equals 1. And so there is my cosine squared and my sine squared. So I get x minus 3 over 7 is equal to cosine of t, and y plus 2 over 6 is equal to the sine of t. We cross multiply, and so we get x minus 3 equals 7 cosine of t, and then our last step would be to add that 3. We're really just working backwards from what we did right here. So if you can do it one way, you should be able to do it the other way. Again, here we would cross multiply. We get y plus 2 equals 6 sine of t. And then we would subtract the 2. And so there is our parametric equations. If you think you're ready to try these, then go ahead and pause the video and attempt to do them as you're working through here. We do have two of the last ones. Since these have minus, I know that these are the secant and tangent one because of the minus. These were plus, so we knew it was cosine squared plus sine squared. That's how you're going to know which one to use. So right here, what's being squared is x over 2 squared, and y over 4 squared is equal to 1. The positive one is going to be my secant, so x over 2 would be equal to the secant of t. And then y over 4 would be equal to the tangent of t. We cross multiply and we get x equals 2 secant t. And here we get y equals 4 tangent t. So those would be our parametric equations right there. The two combined. For this next one, we've got y plus 1 over 4 and x plus 2 over 3 squared. Remember, the positive one is going to be our secant. And so secant of t here is going to be equal to that y plus 1 over 4. And tangent of t is going to be equal to the x plus 2 over 3. We're going to want to cross multiply. And then we're going to want to subtract or add after that. So we cross multiply here. We get 4 secant t equals y plus 1. And then we get 4 secant t minus 1 equals y. On this side, we get 3 tangent t equals x plus 2. And then we subtract the 2. And there is our parametric equations. Ooh. Right there. All right, so on day 1, we practiced getting those parametric equations into graphs and into tables of values so that we could use them. And the big part of that was using that parameter so that we know at what time it is at each location. On the second day, we changed it into word problems so that we can see how that works in real world and we can see if things collide, making sure you know what time each point is where. And then this last one was to get rid of that parameter. So we've gone through the entire parametrics now.